1.9 is just another method for solving linear differential equations. So last class, we learned the method of undetermined coefficients. Today, we're going to learn another new method. It is more applicable. You can solve it for a wider variety of linear differential equations. The method of undetermined coefficients, if you remember, only worked if that function a of t was a constant. Okay, we only were putting numbers there in front of the y. So today, we're going to have a better technique that expands our ability to do this. Okay, it's called integrating factors. We're going to use an integrating factor. So the development of how this technique works is a little like out of thin air. I'm going to go through the development with you. And then once we have it, it's actually pretty easy to put into practice. Okay, but the theory behind it is like, how did anybody come up with that? But it's kind of cool. So first step is subtract a sub t of a of ty from both sides. So we're going to have dy dt minus a of ty equals b of t. And then just to avoid having a lot of negative signs cluttering up our work and having to keep track of them, I'm going to define a new function g of t that just equals a of t. So equals minus a of t. Yeah. So I'm going to do dy dt plus g of t y equals b of t. So just as a simplification, we're going to let g of t equal minus a of t. Just going to keep things cleaner. Okay. When you look at this equation, does it remind anyone of the product rule, the left side? No, me either. But it reminded somebody once, a long time ago, of the product rule, right? Because they were saying, well, could be like y, and g of t could be like the derivative. No, not really. And then dy dt, that's like a derivative. So somebody thought about the product rule when they looked at this one time. So let's just write down the product rule so we can compare it. They were saying this kind of looks like the product rule for if I had taken the derivative of a function y and some other function, which we don't know, we'll call it mu. Okay, so the product rule for y and mu says that d dt of y times mu, okay, where each of those are functions of t, that's y of t and mu of t. Okay. Remember, is going to be mu of t times dy dt. So I'm just going to leave off the of t's so that just to make it a little cleaner. Mu times dy dt plus, so that's the second times the derivative of the first. So now we need the first times the derivative of the second. So d mu dt times y. So there's the product rule of a function y and some other function mu. So if you compare it to this guy, to the left side of this equation, you go, well, we've got the dy dt. If there was a mu there, then I'd have the first term. And here I have the y, right? This y and this y kind of match up. And g of t could be like my d mu dt. Okay. And b of t is just hanging out. That's just on the other side. So I'm just trying to make this side look like the product rule, like if you squint real hard. Yeah, you can see it a little bit. So our next step, to make it look even more like the product rule, is I'm going to take this differential equation and multiply both sides of it by mu of t. That way I can make it look even more like the right-hand side of the product rule. So I'm going to have multiply everything on both sides by mu of t. So I'm going to have mu times dy dt plus mu times g times y equals b times mu. Multiply both sides by mu. Okay, so now this looks a lot more like the product rule. Okay, so I've got the first term, mu times dy dt, matches. And then to make the second term match, the d mu dt times y, to make this term match this term, what would have to be equal? Mu times g would have to equal d mu dt. Okay. So to make these the same, we need mu times g to equal d mu dt. Everybody see where that comes from? So my left terms match, this one and this one match perfect. To make the terms on the right-hand sides match, I need mu times g to equal d mu dt. Yeah, we're trying to figure out what mu I could use. Once we find mu, I could plug it in here, and this would be the derivative of mu times y, which is easy to integrate. Mu times y. You integrate the derivative of something, you get the something back. So let's find mu. Mu times g equals d mu dt. We can do that differential equation because it's separable. So I'm going to do this on a different slide. D mu dt equals mu times g. Okay, so to separate it, divide both sides by mu. So I have 1 over mu d mu equals g dt. And integrate both sides. So I get the ln of mu equals the integral of g of t dt. We don't have a formula for g of t right now, so we can't calculate the integral. And then when I finish solving, just raise e to both sides, so I'm going to get mu of t is equal to e to the integral of g of t dt. Yeah. So mu we can get. Got it. So that's not going to be too hard because it's a nice separable differential equation. But this isn't the answer to our differential equation. This was like a little side trip that we discovered along the way. So if we go back, now we know that this is the product rule. This says mu times dy dt plus d mu dt times y equals b of t times mu of t. And I can rewrite this side as d dt of mu times y, right? That was sort of our whole purpose. We were trying to make it look like the product rule because then we can make it a prettier derivative instead of all this mess. So this guy right here, all of this, that is the product rule, right? We were trying to make it look like the product rule of mu times y. So if you go backwards, right, mu times y, you'd have first times the derivative of the second plus the second times the derivative of the first. So this equals b of t times mu of t. And then just go ahead and integrate both sides. Okay, what is the integral of d dt of mu times y? Mu times y. The integral of the derivative gives you the stuff back. Yes. Mu times y plus c. Yep. Why didn't I write plus c in my notes? Oh, I don't think it is plus c. Because we know that could, yeah. Or, yeah, I guess there is a plus c. I think I'm just going to end up including it in the plus c on the other side. That's what I do. Okay, so mu times y is going to be the integral of b of t times mu of t dt. And that integral we can probably do. We have only t's over there, functions of t. And to solve for y, I can just divide both sides by mu. So I'm going to get y of t is equal to 1 over mu of t times the integral b of t mu of t dt. So that's the answer. That's how you're going to find the solution y of t. You're going to have to calculate two integrals along the way. One to find mu, because mu is a specific function that we found that you would find by doing this. And then once you have mu, you multiply both sides of the equation by mu, rewrite the left side as a product, the derivative of a product, integrate both sides. So these are just formulas, yeah. So I have a summary written on the next page. So we did, I mean, that was kind of a lot of theory, but here's how it works. When you have a differential equation of this form, dy dt plus g of ty equals b of t, first compute the integrating factor mu, and you do that by doing e to the integral of g of t dt. And we only need one integrating factor. We just need one function that will make that product rule thing work. So when you're calculating that integral, just take the most convenient choice for the arbitrary constant, generally 0, right? So you don't need the plus c. Okay. Then you determine the solutions by multiplying both sides of your original differential equation by mu of t and integrating. So let's go through one and see if it works. All right. So we have dy dt plus 3y equals t. First, we need the integrating factor. So I'm going to do that like over here. Mu of t we find by doing e to the integral of g of t dt. Okay, so what is g of t in this case? 3. Okay, so this is going to be e to the integral of 3 dt. What's the integral of 3? 3t. And we're going to take the most convenient choice for c because I only need one integrating function mu. So it's just going to be 3t, no constant, e to the 3t. So there's my mu of t, e to the 3t. Now I have my integrating factor. It's called an integrating factor because then you use it to multiply both sides of the equation. So I have dy dt plus 3y equals t. Multiply both sides of this equation by e to the 3t. So I distribute and I get e to the 3t times dy dt plus 3y, 3e to the 3t times y equals t e to the 3t. Now the left-hand side of this equation, that's the product rule. That's d dt of the product of what two functions? Mu and y. Yep, mu is e to the 3t. So this is d dt of the product of mu and y. Mu we know, y we don't. So this is y times e to the 3t. So this is the key step here, being able to recognize this as the product, the derivative of the product of y and mu. Once you have that, then we can just integrate both sides. Okay, so the integral of d dt of some stuff, it just gives you your stuff back, y e to the 3t. And the integral of t e to the 3t, by parts, yes. So maybe we'll do it on another slide here. So maybe I should write down the formula for how to integrate by parts. Remember that the integral of u dv is equal to u times v minus the integral of v du. So we'll have basically I have to choose a u and a dv from my integrand, and I usually choose u to be the more complicated thing because taking derivatives are easier than antiderivatives. And to use this formula, I have to come up with a v and a du. So what I have is a u and a dv. So if I let u be e to the 3t and v be t dt. Totally did this wrong. Yeah, let's do it the other way. So we'll let u be t and dv be e to the 3t. Right. Choose dv. As long as you can integrate it, you can choose dv to be the more complicated thing. So if we have dv, right, then what is v equal? 1/3 e to the 3t. Great. And if u is t, then du is dt. Or du dt is 1, and then multiply. So now I'm going to use the formula. U times v would be t over 3 e to the 3t. So if u equals t, then du dt equals 1. And then multiply both sides by dt. So I have t over 3 times e to the 3t, that's u times v, minus the integral of v times du. So that would be 1/3 e to the 3t dt, because du equals dt. So I have t over 3 e to the 3t minus, now I have to take this integral. That would be 1/9 e to the 3t. And then just simplify. So I have t over 3 e to the 3t minus 1/9 e to the 3t plus c. No, that's only when you're calculating the integrating factor. Yeah. Oh yeah, I guess it should, but it doesn't really matter. Yeah. So we're not quite done, right? So we go back over here. And now we know that this integral, we just calculated it on the next slide, and it was t over 3 e to the 3t minus 1/9 e to the 3t plus c. Now I have to, just to finish solving for y, divide both sides by e to the 3t. So we get y equals t over 3 minus 1/9 plus c e to the negative 3t, or c over e to the 3t. No, because t is a variable. That's not a, yeah. If it just said e to the negative 3, then that would be a new constant. If you had an initial value, that's when you would find the c. Because nope, because the constant, yeah, what makes this family of differential equations isn't a plus c at the end. It's a coefficient on this e. So this minus 1/9 makes a difference. Because if there was just a plain old plus c at the end, then I could mush them together. It's kind of a long process. 2 integrals plus answering the question, right? So should we do another one together, or do you want to try the next one? Let's do another one. Yeah, on this one we could, because the coefficient on the y was a constant, right? It was a 3. It might have been, yeah, yep. But I wanted to start with an easy example to show you the method. Yep. All right, so let's do another one together. Okay, so we have, this is in the correct format. It's dy dt plus g of t equals b of t. Okay. So we start by coming up with an integrating factor, mu of t. Mu of t, remember, is e to the integral of g of t dt. So this is e to the integral of 2 over t dt. What's the integral of 2 over t dt? 2 ln t. So this is e to the 2 ln t. And I don't need the plus c, because I just need one function that will create my product rule. Don't need a whole family. Yes, it does. Yeah, so first we have to write this as e to the ln of t squared. If you remember that property of logs. Yep, when you have the coefficient in front, you can pop it up on the exponent. And then e to the ln of some stuff. E and ln are inverse functions, so this is just t squared. Yeah, looks nice and easy. All right, so rewriting my equation. I'm going to multiply both sides of it by the integrating factor t squared. Okay, so I have t squared dy dt plus 2ty. Just distributing my t squared. T squared over t cancels to a t. And then that equals t cubed minus t squared. All right, the left-hand side of this equation is the product rule. It's d dt of the product of which two functions? Y and mu in this case is t squared. So this is d dt of t squared y. So I'm using the product rule in reverse. I'm recognizing this as having done the product rule on t squared times y. Now integrate both sides. Integrate, integrate. And the integral of the derivative, they cancel, and I get t squared y. And there's technically a plus c, but I'm going to smush it into the plus c on the other side. So this is going to become t to the 4th over 4 minus t cubed over 3 plus c. Right, and now I divide both sides by t squared. So I have y equals t squared over 4 minus t over 3 plus c over t squared. That is the general solution to my differential equation. Yeah, that one was nicer. I should reverse the order for next time. Yeah. Like, oh, it's not as hard after all. Yeah. Okay, before we do this mixture problem together, I really want you to do this method once on your own. So I'm going to have you jump to the practice and do, I don't know, which one of these is easy? Just do number 1. Do number 1. Let's do it together because everybody's coming up with varying answers and they're not matching mine, which doesn't mean that people are wrong. Mine could be wrong. All right, so we start with mu of t. You do have to do by parts twice, yeah. Okay. So I have mu of t is e to the integral of g of t dt. So this is e to the to the integral of negative 2 dt, which is e to the negative 2t. Okay. So now multiply both sides of the differential equation by mu. So I'm going to have e to the negative 2t, oops, e to the negative 2t times dy dt minus 2 e to the negative 2t y equals t squared. E to the t times e to the negative 2t would be e to the negative t. Because you have like bases, you can add the exponents. Okay, so now recognize the left side of this differential equation as the derivative of the product of y and e to the negative 2t. Okay, so now integrate both sides. And I have y e to the negative 2t equals the integral of t squared times e to the negative t dt, which is going to necessitate doing by parts twice. So let's just do it on another slide and we'll leave this one clean and come back and put the answer in once we have it. Okay, so the integral of t squared e to the negative t. Okay, so we'll let u be t squared and dv be e to the negative t. And then I'll find du is 2t dt and v is negative e to the negative t. So now just apply the formula for integration by parts, and it's u times v, negative t squared e to the negative t, u times v minus the integral of v du. So negative 2t e to the negative t dt. So this was a subtraction sign and there was a negative on my was that v du. There's a negative on my v, so I just made it into a plus sign here. Okay. Now I have to do by parts again to solve 2t e to the negative t. So I will let u be 2t, dv be e to the negative t. So du is equal to 2 dt, And v is negative e to the negative t. So I have negative t squared, e to the negative t, plus, now I'm going to do this whole integral, which would be u times v, 2t e to the negative t, minus the integral of u times v, you're right, yep, that's negative, so I'll just do that. U times v, yeah, minus the integral of v du, so I can make that a plus because I have a negative. U dv. Nope, that is still minus. There's no minus sign. U dv, there's no negative sign here in u or dv.
No, it's du.
Oh, u times v minus v du. Right, so yeah, there's a negative. V du, so I've got 2 e to the negative t dt. Okay, so then that last one is not too hard to integrate. And I have negative t squared e to the negative t minus 2t e to the negative t. And then the integral of this would be minus 2e to the negative t plus c. And can I combine any terms here? E to the negative t is in everything. I could factor that out. It does? Okay, well. It's okay. I don't think it'll help. I'm gonna go with this one. So t squared e to the negative t. Oh, thank you. Plus c. Okay, and that all equals ye to the negative 2t. And divide both sides by e to the negative 2t. And we get y equals negative t squared e to the t minus 2t e to the t minus 2 e to the t plus c e to the 2t. Okay, my answer was wrong. I don't know where I got that. Sorry. So the same amount is going in as is coming out. And at time t equals 0, the water flowing into the pond from stream A becomes contaminated with road salt at a concentration of 5 kilograms per 1,000 cubic meters. And the water in the pond is well mixed, so the concentration of salt at any given time is constant. And also at time t equals 0, someone begins dumping trash into the pond at 50 cubic meters per day. The trash settles to the bottom of the pond, which reduces the volume of the pond by 50 cubic meters. So to adjust for the incoming trash, the rate that the water flows out increases to 1,300 cubic meters per day. Yeah. All right, so we want to write a model for S of t, the amount of salt in the pond at time t. And then if you want on your own later, you can solve it by using an integrating factor. Okay, so S of t, the amount of salt. Okay. So I'm going to write a differential equation, ds dt. The rate at which salt, the amount of salt is changing in the pond, would be equal to the rate salt enters minus the rate that salt leaves. And then we have to calculate each of these separately. I'm going to do a little work on the side to figure out what these expressions should be. So the rate that salt enters to get a rate, we're going to do concentration times speed. Okay, so concentration, which we would measure in kilograms per cubic meter, times the speed that the water is coming in. Speed of the water, which is measured in cubic meters per day. So then, this is kilograms of salt, right? Okay. So my cubic meters are going to cancel, and I'm going to end up with the rate that salt enters in kilograms of salt per day. All right, so what is the concentration of the salt entering the pond? Yeah, 5 kilograms per 1,000 cubic meters. So 5 kilograms per 1,000 cubic meters is given in the question. And then the speed that water is entering, 500 cubic meters per day. Cubic meters cancel, and we get zeros cancel. 25 over 10, 2.5 kilograms per day of salt. So I go back to my differential equation, and I'm going to put in a 2.5 right here. All right, now the rate that salt is leaving, let me get a new page here. Same thing, it's going to be concentration times the water speed. So how do I measure the concentration of salt in the whole pond? There is trash. No. Yes, so this would be amount of salt divided by the volume of the pond. And then we multiply that times the speed with which water is leaving, and that is what? Close. It actually speeds up once we started dumping trash to 1,300 cubic meters per day so that the pond won't overflow. So this is actually 1,300 meters per day. Okay, amount of salt in the pond. Well, if we knew that, we wouldn't be writing an equation. That's what this equation is solving for, S of t, right? Mm-hmm. The rate of water. So I hear what you're saying, yes. It would make sense that the outflow would have to get faster and faster to keep it from overflowing. Oh, right. So that's fine. Yeah, that's fine. Yeah. So the amount of salt is S. That's what we don't know. That's what we're trying to solve for. And then the volume of the pond is changing over time, right? Because we're putting garbage in. So the volume of the pond is shrinking by 50 cubic meters per day, and the pond started out at 10,000 cubic meters. So this is going to be 10,000 minus 50 t. T is the number of, t is time, our variable time in this equation, times 1,300. Cubic meters are going to cancel, and I'm just going to end up with kilograms of salt. So if you simplify this expression, I'll spare you the algebra. It comes out to 26S over 200 minus t. That's kilograms of salt per day. Yeah. So we go back and put that into our differential equation as the rate that salt is leaving the pond. 26S over 200 minus T. So there's our differential equation. To fully solve this, I need an initial condition, which would be what? S of 0, which is the amount of salt in the pond at time 0, 0, because they told us that the pond started clean. I know. So there's our differential equation. To the other side, and that will be your G of T. Yeah.